Good afternoon, students. Today I will discuss some mathematical preliminaries required to do the problems that you have encountered, that you will encounter in this course. So, I will be giving a couple of lectures on some important mathematical results which are handy if you are dealing with numerical problems. So, very simple. So, I am going to title this lecture as mathematical prerequisites. You can skip these prerequisites if you are already familiar with them, but just in case you are not familiar, this might turn out to be useful. Okay. So, a couple of things that I will discuss, I am going to write them down. So, one is to compute how to compute a Gaussian integral. So, basically we are looking to integrate a function from minus infinity to plus infinity, and the function here is the Gaussian function. Okay. Let us say this is I, fine. So, this is the first problem on the agenda. Second, I will discuss an important technique which is the saddle point approximation. That we will be using in the second chapter of statistical mechanics. Is basically a very important approximation method, and if you want to approximate the sum of exponentials. So, suppose I have exponentials I going from 1 to some t number of terms, and I have these exponentials of the type e raised to n times some x of I. Okay. So, these all these terms here are positive because they are exponents, they cannot be negative. So, they are all positive in nature, each term is positive in nature, and the exponent is some n times x I. Okay. So, I will show that saddle point approximation says that I can approximate this sum as just the maximum of the terms. So, suppose the maximum term in this expression is e to the power n x max, then I can approximate the entire sum with the maximum of the terms if n goes to infinity. Okay. So, if you encounter a sum of exponentials where each exponential term has a power n times x or n times some function of x, then as you take n to infinity, you can approximate this sum as e raised to n x max. Okay. So, this is a very important approximation that I will be discussing today. The third thing that I want to discuss is that of Fourier transform. So, some important Fourier transforms that you have encountered in chapter 1. You will be encountering Fourier transforms everywhere in theoretical physics. So, I am not sure how much of the background you already carry in the context of Fourier transforms, but we will take some simple Fourier transform examples. And for example, I will take a function that you have encountered in this course, which is the Lorentz distribution or a Cauchy distribution. So, we have taken this as a distribution. After proper normalization, it came out to be some a by pi into 1 by a square plus x square. So, here a is constant. So, I will take the Fourier transform of this function. So, let us say our function is defined as p of x. So, we will compute the Fourier transform of this function, which is defined as x going from minus infinity to plus infinity p of x e to the power I k x dx. And the last topic of this lecture would be to compute some important Laplace transforms. I have discussed Fourier transform, I will take one example of a Laplace transform and show how it is very important to construct important results. Okay. So, Laplace transform is defined. So, if you take a function, let us say you take a power law x to the power n, then the Laplace transform of this function is defined as an integral x going from 0 to infinity e to the power minus s x x to the power n dx, and naturally this is a integration on x, a definite integration on x. This result is nothing but a function of s and with a parameter n. Okay. And we will show that this is equal to n factorial over s to the power n plus 1. Okay. And derive an important result that your n factorial is nothing but this function at n equal to 0, at s equal to 0. Okay. Our Laplace transform, yeah. So, this function would be at f s n taken at s equals to 1, which we also call sometimes as the gamma function. So, that is a definition. Okay. It is gamma n plus 1 is called as n factorial, which means if I want gamma n, this would be just n minus 1 factorial. Okay. Or you can use whichever definition you want to choose. So, let us start with the Gaussian integral, okay, the first topic on our agenda. So, we will first start with the Gaussian integral, because you will encounter this many places. So, we have the integral which is basically x going from minus infinity to plus infinity e to the power minus a x square. Okay. So, if you want to understand what is a Gaussian function, well, this is a Bell function. So, the way I have written my function, it peaks at the origin, and it has a, if you understand this as a probability distribution function, then its mean value is 0. So, this is the bell curve or the Gaussian function, and the integration of this Gaussian function is the agenda of our discussion. So, I am going to make a small trick here, that if I want to compute I can instead calculate I square. Okay. So, I am going to write down I square as the integral x going from minus infinity to plus infinity e to the power minus a x square dx, and square it up, which means I can write it as some y going from minus infinity to plus infinity e raised to minus a y square dy. The reason being x and y are independent coordinates, they are the coordinates that are integrated over. So, they are being they are serving the purpose of a dummy variable. Okay. So, neither is this integral a function of x and neither is this integral a function of y, which means I can keep the integration variable as x, y, z or anything. So, okay. So, it is just a function of A, and this is also a function of okay, just a function of A, and this is also a function of A. So, this allows me to write down this square as two separate definite integrals, and now I can combine these two definite integrals and use a double integral, one for x and one for y, and I can take the integrand and combine it as call as e raised to minus a x square plus y square dx dy. And then actually I can pause here instead of proceeding further, and notice that this is nothing but an area integral. Okay. So, I have taken a function e raised to minus a x square plus y square, and I am doing an area integral of this function. So, I can make some substitutions already. So, I know in 2 dimensions, and this is a 2 dimensional integration. So, if I take this as my x axis, and if I take that as my y axis, okay, then any small area element that I can consider here, some small area element would be just dx dy, and I can simply integrate over the entire space. That would be my total area. So, I can write down my area element dx dy in polar representation as simply dr into r d theta. Okay. So, if you want you can think of this as my small increment in the direction of unit vector r, and this is a small increment in the direction of unit vector theta. So, whether I use the Cartesian components or if I use the r theta components, the displacement components are dr and r d theta if I go into the polar components, and hence I can write down my x square plus y square as the length r square. Okay. And similarly, the limits on the integration will now become, so my integration which is I square now becomes, this double integral that I have written is now over integral r, that is going from 0 to infinity, because if I look into this figure to compute an area integral, at location r, what I need to do is basically take my aerial vector, aerial displacement, okay, at various points in my surface, and at each point this would be nothing but a aerial element located at coordinates r comma theta. Okay. So, theta here will go from 0 to 2 pi, and the location would be just specified at a distance r from the center. Okay. So, then I can simply write down my theta to go from 0 to 2 pi, okay, and this particular integrand is just e raised to minus a r square, and I can write down this element dx dy as what I have written here, okay, r into dr d theta, fine, and then simply take the theta integration first. So, that would simply give me 2 pi, and the integration on r would become just e to the power minus a r square into r dr. Okay. And by substituting r square as just u by a, okay, I can write down twice r dr as just 1 upon a into du. So, this will give my I square as 2 pi into integration 0 to infinity, because the limits on r are the same as limits on u, and I get e to the power minus u into 1 upon 2 a du. So, this will give me just pi by a integration 0 to infinity e raised to minus u du, and that is nothing but pi by a this will give me just pi by a. Okay. And then I can write down I as square root of pi by a. Okay. So, this is the Gaussian integral that we were chasing. That is the result of the Gaussian integral. So, our next problem in the agenda is to use a saddle point approximation, and we can do this So, this was an important topic that we deferred for a separate lecture, and you have to recall some of the concepts that we discussed in the second chapter, where we have used the saddle point approximation, especially in the computation of entropy for an ideal gas system. So, I will describe this as just an approximation for a sum over a large number of exponentials. So, if I have t exponentials and if I sum them up, and here each exponential is of this form, e to the power some n times a function of x. Let me take this as a function of x. The simplest function of x is x itself. You can take any function of x here, and the index I here is just f of x I. Okay. So, you can take f of x as simply x, then this becomes just a summation over, then my s simply becomes summation over I going from 1 to t e to the power n x I. Okay. You can take f of x as x square, then your summation becomes I going from 1 to t e to the power n x I square. You can take any function basically. So, what I am going to do is take any function f of x and simply simply sum over various values of x and take t such terms and add them up. The argument is I can approximate s by the largest term in this sum, and the largest term would be the term which is at the maximum of f coming at some x star. Okay. If n tends to infinity. Okay. So, we can do this very simply by saying that look, my sum was composed of a large number of terms. So, I am going to write it as if I am writing my original sum as a sum over all these exponentials as f at x1 plus e to the power n f x2 okay, and the last term being okay. So, I can definitely say that my summation would be less than e to the power n f max at some x star. Let us say one of these terms is the maximum and it occurs at x star. Okay. So, I definitely know that my sum is less than that, and I can definitely say that my summation. So, this is very clear, and it is also I have to say that this, in fact, I have made a small error here, it has to be definitely greater than, okay, and it has to be definitely less than. If I replace each term in the summation by the maximum, then what I would get is just n times if I replace each term by the maximum, then I would get t times the maximum. Okay. So, then I can say that my S is less than, it is definitely less than t times t being the total number of terms. If I replace each term with the maximum, then definitely it is over counting my sum. And if I just take the largest in the sum, then definitely my x is greater than that. Okay. So, this gives us this very nice inequality. Now, you can do a couple of things here. You can take a logarithm on the entire inequality. So, taking logarithm, natural logarithm, okay. So, taking natural logarithm, you would get n times f maximum at some x star, okay, which should be less than natural log of s which should be less than natural log of t plus n times f max at some x star. Fine, you have taken a natural log throughout, and natural log to the base e of e is 1. Now, you can divide throughout by n. Okay. So, if you divide throughout by n, what you get is nothing but the maximum of the function at one of the values of x, let us say that is x star, is less than ln s over n, is less than ln t over n plus f max at some x star. Now, this is where it gets interesting. If you take, and which is always possible, so I will say taking, not if, but I will say taking our T, the total number of terms, as some power of n, okay, which is always possible. Suppose you take for example, you have total 100 terms, okay, and your number of, you can say your big N is 100, then I know A is equal to 1, because 100 to the power 1 is 100. Okay. So, that is one case, but if I take let us say you know, so this would give me A as 1, but if I take N as 1000, okay. Okay. So, here I can get my A to be so I can compute my A as simply 100 equals to 10 to the power 3 times raised to the power A. So, if I take a ln on both sides, this would be roughly 2 and this would be just A into 3. So, I can say that A should be 2 by 3. Okay, because 1000 to the power 2 by 3 is 100. So, this way you can take any n and always find that you can raise n to some power and get the number of terms that are required roughly to an order. Okay. So, then I can always write down my inequality that is written above. So, this inequality is now recasted as with the substitution t as n to the power a, you can write it as f maximum at some x star, this will be less than ln s by n, which should be less than a ln n by n plus f maximum at x star. Okay. Now, you can see that for large n, which is the case that we are chasing, I can ignore ln n by n, simply being suppose you take n as 100, then ln n by n is roughly 2 by 100 and if you take n as let us say even larger 10 to the power 6 or 8, some larger number, then you know, you can say that ln n by n is an even smaller number, this would be just 8 by 10 to the power 8. So, as you take n to be very large, which is typically the number of particles that you would have in a system, and then in the limit of such large n's, you can always drop ln n by n, okay, because that is going to be a number of vanishing magnitude. So, I can then recast my inequality here, okay, as simply, so this gives us as n goes to infinity, okay, f star f max at x star less than ln s by n, which is I am going to drop my a ln n by n and simply write this as f max at x star. Now, you can see that ln s by n is now bounded from above and below by the same number, which is f max, and this is only possible if I write down ln s as it takes the value one of them, because it is bounded from above and below by the same number. So, I will say that ln s by n is equal to f max at x star. Okay. I am going to use an approximation here because you have dropped ln n by n in the approximation that n goes to infinity. So, then we can write down our s as simply e to the power n times f max at x star. So, that completes our saddle point discussion. Okay. So, this is the this is a very important equality or approximation that we can use in the limit of large n. Right. So, we will go to the next topic, which is if you recall, this is like taking Fourier transform of a function, and as an example I have taken a Lorentzian function. So, let me take its Fourier transform. Right. So, one of the important mathematical techniques is the technique of Fourier transform. So, we will take our function in such a way. I am given a function with the motivation that is follows, this function will require you to compute the Fourier transform by the method of contour integrations. So, it is like hitting two birds with one arrow. So, we will also learn something about contour integrations here. So, the Fourier transform of this distribution function, which is also called as the characteristic function of this distribution, and that you will see in the chapter 1, is nothing but the limits x going from minus infinity to plus infinity, p of x e to the power I k x dx. Now, you must have taken some course in Fourier transform, but if you have not, then the take home message is that you have a function that is required at each points in the direct space, in this case p of x, and the Fourier transform will then give me the function in the Fourier space at one value of k. So, if you can see, a function p of s is taken at all values of x from minus infinity to plus infinity to generate one value of the Fourier amplitude at mode k. The inverse transform would mean that I will get my function at one value of the direct space by simply taking a inverse Fourier transform. That means my Fourier amplitudes have to be known everywhere in the k space. Okay. So, if I know the Fourier amplitudes everywhere in the k space, then I can compute the inverse Fourier transform, recover the function. So, all x giving me 1 k and all k giving me 1 x is the logic here, and usually the function that we are in fact almost always the function that we take for Fourier transforms are aperiodic functions, because Fourier transforms are derived from Fourier series in the limit when the function ceases to become periodic or fails to complete one cycle. Okay. So, in distinction to Fourier series, which applies to periodic functions in a box of size L, Fourier transforms are useful for functions which are aperiodic. Okay. So, let us compute the Fourier transform here. So, you can I will take the Fourier transform and leave the inverse to you. So, this would be just integral x going from, we are computing the Fourier transform. So, x going from minus infinity to plus infinity. Now, our function is a by pi into a square plus x square into e raised to I k x dx. Okay. So, this can be written as a by pi into integration of minus infinity to plus infinity e to the power I k x over a square plus x square. Now, I expect that you have taken some course on complex variables, because I will be using a complex integration to compute this integral. So, I am going to call this as integral 1 and say that instead of computing this integral, I will compute some integral in the complex plane, which is nothing but a contour integral of e to the power I k z over a square plus z square dz. So, I must indicate my contour here. So, the contour that I am using is basically, so this is my complex plane and I am using a semicircular contour, and this is the direction of my contour integration. This is my x axis, this is my y axis, and there are two poles of this function. So, the function has the integrand it has, I can rewrite this integrand to show that it to basically expose its poles. It can be written as e raised to I k z upon z plus I a into z minus I a. So, there are two poles, I am going to use only one of them, which is at a, and there is another pole at minus a that I am going to drop. Okay. So, as you can see, okay. So, then I can easily write down my contour integral. This would be nothing but 2 pi I into the residue at z equals to I a. Okay. Only the contour in the, only the residue inside the contour that is drawn. So, this would be nothing but the residue at z equals to I a would be nothing but would be nothing but, if I just substitute z equals to I a, it is a simple pole. So, all I have to do is just substitute z equal to I a there. So, it will give me e to the power I k into I a divided by 2 I a, just substituting z equals to I a in my function. Okay. So, the residue here is at any z naught is nothing but limit z tending to z naught into your function. Okay. So, you multiply z minus z naught, which is z minus I a, and that would be just e to the power I k z upon z plus I a. In that you substitute I a, that would give you your residue. So, this would be nothing but pi by a into e to the power minus k a. Okay. Fine. Now, there is something that I would like to mention here. My contour integral e raised to the integral of e raised to I k z upon a square plus z square can also be written as a sum of two integrals. So, I can write down there is a line integral here and there is a contour integral here. I will call it as C A and I am going to call this as C L, the straight line part. Okay. So, I can write my contour integral, which is e to the power I k z over z square plus a square d z, okay, as simply the straight line component, which is going from if I call this point as plus r and this point as minus r, this is a circle of radius r, semicircle of radius r. Then the straight line part goes from x equals to minus r to plus r, okay, that is my C L. And here my function is e to the power I k x dx over, because z is just x here, okay, plus I will have a part where if you look at the contour here, the only degree of freedom is theta, because r is fixed here. So, I can call my complex variable z on this contour as simply r. Each point on this surface is on the circle is just r e to the power I theta, okay, that is my complex variable. So, here theta goes from 0 to pi, and this is my contour C A, the arc, the pi arc, and here my function is nothing but e to the power I k, and the complex variable is r into e raised to I theta divided by z square is nothing but r square e to the power 2 I theta plus a square, and dz would be nothing but r I e to the power I theta d theta, okay. Since I have taken z as r e raised to I theta, dz would be r I e to the power I theta d theta, because r is not constant, r is constant, only theta varies on that semicircle. So, now you can see that this contour integral, if I am going to just consider this one, you can see that it can be written as theta going from 0 to pi. I can split up the numerator as e to the power I k r cos theta into e to the power minus k r cos sin theta, because e raised to I theta is cos theta plus I sin theta, I into I gives you minus sin into r I e to the power I theta d theta divided by r square e to the power 2 I theta plus a square, fine. So, as you can see, as for k greater than 0, I know in the quadrant that I am doing my integral, the first quadrant and the second quadrant, sin theta is always positive. So, if k is greater than 0 and sin theta is always positive, okay, because I am in the first and second quadrant. Then as r goes to infinity, I can see that my numerator goes to 0, okay, because it is going as e to the power minus r into r, and the denominator is going as r square. Okay. So, the denominator will become larger and larger, the numerator will go towards 0. This means my overall integral here will only go towards 0, its magnitude will go towards 0. Okay. So, the numerator is going as e raised to minus k r into r, that will go to 0. The denominator is going much faster towards the denominator is going as quadratic in r, but towards infinity. So, the ratio of numerator over denominator will definitely go towards 0. And so, if I take a bigger circle and even a bigger circle, eventually if I take my semicircle at infinity, my function remains analytic, e raised to I k z remains analytic, because that is going towards 0, okay. But its integral on the contour on the arc becomes 0, which means I can say that the residue does not change, the residue is unmoved. So, the integral I z as r goes to infinity remains the same. So, it remains pi by a e to the power minus k a, okay. And I can write down for a fact that the integral on the arc goes to 0 as long as k is positive, which means I can write down my integral, this part, the CL part, okay, that. So, I can now write down the entire thing as limit r tending to infinity minus r to plus r e to the power I k x over a square plus x square dx plus theta goes from 0 to pi e to the power I k z dz over a square plus z square, and I have just shown that this integral is basically pi by a into e to the power minus k a. So, as r goes to infinity, if I want to drop this term, then I have to change my k to positive. So, I have to write down two things happen. One is that this straight line integral becomes minus infinity to plus infinity e to the power I k x upon a square plus x square dx, and what it does to my right hand side is that it makes my k always positive. So, I have to take it as minus of mod k into a, because only then I can put this semicircular contribution to 0. Now, combining this with what I wanted, so what I wanted is basically a factor of a by pi outside in equation 1. So, my Fourier transform is basically a by pi into pi by a e to the power minus mod k to a, which is nothing but e to the power minus mod k into a. That is the answer. Okay. You could have taken the bottom circular contour also, but that would have given you an integration from infinity to minus infinity with a negative sign. So, it gives you the same answer whatever contour you take, fine. And this brings us to the last topic in the discussion, which is a gamma function. So, or I will introduce the gamma function from Laplace transforms. Since I have already taken Fourier transform, an example in Fourier transform, I will take one example in the Laplace transform. So, Laplace transforms and Fourier transforms are connected in the sense that if you are unable to take a Fourier transform of a function that diverges in the limits, then you can pad this function only on the positive side and take a Laplace transform for the imaginary frequencies. So, they are related to each other. I will skip the background of Laplace transform, except that I will tell you what Laplace transform mathematically means. So, if you want to take a Laplace transform of some function, then it basically amounts to taking this integral 0 to infinity f x e to the power minus s x dx. Now, since this is a definite integral on x, the answer is a function only of the s, which is basically your frequency, imaginary frequency or imaginary wave vector, depending upon whether you take x as displacement or time. Okay. So, it is just a function of s. Okay. So, now if I take for example, if I take our function as some x to the power n, okay, then the Laplace transform of my function is nothing but Laplace transform of x to the power n, and this will be nothing but a function of both my variable s and the parameter n, because it is defined as an integral x going from 0 to infinity x to the power n e raised to minus s x dx. Okay. So, this is very simple. We have computed Laplace transforms in the grand canonical ensemble, I think the Gibbs canonical ensemble, and so this is basically going to help you if you are not aware of how to take Laplace transform. So, here this is I will take a simple example which is x to the power n. So, you can write down this as in the form of a recursion relation. So, this is just x going from 0 to infinity x to the power n e raised to minus s x dx. Now, to solve this you have to do integration by parts, and I will encourage you to take this as the first function x to the power n as the first function and e to the power minus s x as the second function. For the reasons are simple, each successive derivation of x to the power n reduces its order of derivative. That is the encouragement to take this as the first function. So, you take this and perform the integration by parts. What you get in the first term is x raised to n e raised to minus s x over minus s, and you apply the integration limits plus n by s into the integration x to the power n minus 1 e raised to minus s x dx. Okay. Now, look at the first term. At x equals to infinity, e raised to minus s x will go to 0. Of course, x raised to n will go to infinity, but you can easily show by L'Hopital's rule that x raised to n e raised to minus s x will go to 0. And for x equals to 0, which is the lower limit, the exponent becomes 1, but x raised to n becomes 0. So, this is overall 0 at both the limits. First limit you can show by L'Hopital's rule, second limit you can just show directly. But what is left over now is interesting, it is n by s multiplied to the Laplace transform of x raised to n minus 1. Okay. So, this way if you continue, so if you take one more Laplace transform, it would be n by s into n minus 1 by s into Laplace transform of x raised to n minus 2. And if you keep continuing, what you will get at the end of the overall steps would be n by s into n minus 1 by s all the way to n minus 2 by s, and the last term would be 1 by s into Laplace transform of x raised to 0 or 1. Okay. So, basically what you have here is nothing but n factorial over s to the power n into Laplace transform of 1, which is nothing but Laplace transform of 1. If you look at the definition, just put n equals to 1 here, you will get just 1 upon s. Okay. So, this will be n factorial over s to the power n plus 1, and that is the Laplace transform of x raised to n, and this is a function of s and n. Okay. So, the definition of n factorial is also the value of this function, the Laplace transform taken at s equals to 1, and this can be also defined mathematically to be as a gamma function in such a way that gamma n plus 1 is always n factorial. It is just a definition, nothing more than that. Okay. So, you can always, since n factorial is equal to n into n minus 1 factorial, I can call this as n into gamma n. Okay. And this is nothing but gamma n plus 1. So, that is how you form a recursion of gamma function. So, n gamma n is gamma n plus 1, right. So, this is how we compute gamma functions or n factorials. All right. So, this is where we end and when we meet in the next class we will have one more mathematical preliminaries where I will discuss some more important useful integrals, and we will take it from here.